Hey everybody, welcome to day 10 of assembly language class. First I wanted to start by reminding you we've got an exam on later this week, starting on Wednesday and with a window going until Thursday. I wanted to see if there are any questions about the exam. I posted some material at the start of our, or down at the bottom of our Moodle page describing how the exam is going to go. And of course, you've got a lot of old exams to use as reference material. I'll say again, the window for the exam will go from first start of the day on Wednesday till the end of the day on Thursday, where start of the day is defined as 8 a.m. Eastern time, and end of the day is 5 p.m. Eastern time. That'll give you still a pretty good window to take the exam. Any questions before we get started with today's material, especially about the exam? 1,000. All right, so it sounds like everybody feels pretty good about the exam. Hopefully the materials that are posted will help you be ready for that. Today might end up being a little bit of a short lecture. We've got material on testing that we're going to talk through, so we'll get through that. We won't really be learning new assembly language stuff today, except that some of what we'll talk about with testing might apply in particular to assembly language. All right, so today we'll be talking about some terminology with testing, different approaches to testing, and different kind of common ways we can test our systems and measure how good of a job we're doing with testing. Testing is a important part of any software project. I guess I usually get to work with the senior design class at NC State. And that's a place where we try to bring together everything that they've learned across their 4 years as a student in computer science. And it's hard to get even then, after they've taken a number of courses and probably written a lot of bugs into the software they've created, it's still hard to get students to appreciate the value of testing. It's easy for them to decide that that's kind of a secondary concern, and that writing code is the biggest part of their responsibility. That's understandable. I think it's exciting to add new features, but it's also good to appreciate that having a working piece of software that you can have some confidence in might be important, especially to the success of your software project and to the safety of others. And we'll talk a little bit about that. In testing, we'll often we'll be concerned about validation and verification. And those are two terms that people readily get confused because they both start with V. Validation in general is the idea, are we building the right, trying not to just read from my slides here, are we building the right thing? Are we building the thing that our customer wants? Do we understand things like requirements correctly? Verification, so validation, often you'll hear people say, are we building the right thing? Are we building the right product? Sorry, I hope I said that right. Let me say it again. Validation is the idea, are we building the right thing? Are we building the right product? As opposed to verification, which you'll often hear people say as, are we building the thing right? Are we building it correctly? The thing that we're building, the software that we're designing, the code that we're implementing, is it consistent with the specifications we've come up with? Is it consistent with the requirements? If we've done validation, then we figured out what we're supposed to build. And then when we started building the thing, whether we're designing it or whether we're actually writing code, are we building a thing that does what it's supposed to? Are we building a thing that works under all circumstances and meets the specifications that we agreed with the customer on? These are, and I'm struggling with the language here a little bit because it's not strictly a transition from one phase of software development to another where you worry about this. Things can go wrong with this at every stage. You imagine that you start out with requirements, you try to figure out what you're trying to build. And then from that, you might go to a specification, a detailed description of what your system is going to have to do. And then from that, you might go to a design, a description of how you're going to build the thing that you're building. And from that, you might go to an implementation. And validation and verification questions are things you can ask at every one of those stages. Is what you're doing at this stage consistent with what you understand from the previous stage? So this isn't something that we do just when we're talking to the customer. One way that we try to understand if the software we've built is functioning correctly is we look for faults in the software. We look for things that go wrong. This is a picture that's trying to show kind of the space of all possible states of our system, all things that it could do. You can think of this as all possible inputs that we could give our program. And for realistic programs, we can't test this entire space. So if you think of a program that had to do something simple, like multiply two integers, well, it might not be feasible to test all possible pairs of integers to give to that program. So in general, when we're testing a system, we kind of have to spot check it. And that's what this picture is trying to show. If you think of the big blue bubble as these are all possible things our program might have to deal with, all possible states or inputs it might have to worry about. The yellow dots are like the things we're going to test. We'll try to test it on various inputs. We'll try to give it those inputs and see how it behaves and try to make sure that those are right. And the point here is we can't test everything. But when we're choosing the stuff that we're going to test, we can try to be smart about that. If you think about all possible behaviors our program might be expected to exhibit, and you think about the particular cases that we're going to test, they tend to fall into particular groups. And thinking about those groups can help us try to design tests that cover the space of possibilities in our program's behavior. And that's what this figure is trying to illustrate. If you imagine that you've got all possible behaviors for your program, all possible inputs that it might be exposed to, and you're just going to spot test some of those. If you can think about the inputs as falling into particular categories, you can at least make sure that you've covered those categories. So if you think of the way this is broken up as these represent different behaviors, or I'll say different equivalence classes of inputs. You need inputs that are like this. You need inputs that are like this. You need inputs that are like this. In designing your tests, you want to at least cover all of those equivalence classes of behavior. We're talking about this in the abstract here, which maybe makes it kind of hard to talk about. Let's pick a particular case, and then maybe that'll make it easier to think about what we were just talking about. So let's pretend we had to write a function that computed the greatest common divisor of two integers. There's pretty good algorithm for this. I think it's Euclid's algorithm. Even without that, you can still think of what this function is supposed to do. You give it two integers and it finds the biggest value that divides them both evenly, or I guess said backward, the biggest value such that each of those two integers is a multiple of that value. So it's an even integer multiple of it. Now this, if you wanted, let's say you had written this function and you just wanted to test that one function, there's a lot of inputs you could give it. I guess it depends on what you think int means. Even if you believe int is just a 32-bit integer value. Well, there aren't really, if you restrict the inputs to just 32-bit signed integers, then well, there aren't infinitely many inputs, but there's still probably so many that you're not going to be able to test this function exhaustively. But in thinking about the greatest common divisor algorithm, there are probably some important cases that you need to make sure you cover. And backing up a slide, that's what we're talking about here. If you think about all the different kinds of input you could give the program, you might have to worry about, well, we need to give it this kind of input and this kind of inputs. So for GCD, greatest common divisor as an example, You could just make up so one case might be, it's called the common case here. I guess I would say it's the nothing special case. You could just give it a pair of inputs that have a greatest common divisor probably bigger than 1, so an interesting case there, and make sure that for at least some cases like that you've tested, and that you make sure the function's returning the right output. You could consider special cases. So for GCD, it's possible that one of the values is the GCD, is the greatest common divisor of both of the numbers. So if the input, like that second line, if one of the inputs was 2 and the other input is 4, well, in that case, 2 itself is the greatest common divisor. So you might want to test with that. In fact, you might want to reverse it, making sure that you can handle both the first value and the second value happening to be the GCD. If the two numbers are prime, then their greatest common divisor is 1. So you might want to test an input where the two numbers are both primes. You could even have numbers where their greatest common divisor is 1, but they don't happen to be primes themselves. And we'd call those mutually prime numbers. They don't have any common factor bigger than 1, even if they don't happen to be prime. So you can make sure you test on those. You could also think about problematic cases, or cases that might not even be valid inputs, but you might want to at least decide what the program should do, what your function should do in that case, and make sure that you get the expected behavior. Cases like if one of the values is 0, then the greatest common divisor is probably not going to be meaningful. And if one or both of the values are negative, you've got to decide what GCD means in that case, or if perhaps that's not a valid input. There was a question that popped, or there was something that popped up on the chat. Does anyone have a question? All right, moving on. So here, some of the same thing we talked about. In general, testing a system can't be tested on every possible input. And we just said that. I added the generally to this slide because I could imagine some special cases where you could test a function on every possible input. Like if you just passed it some Boolean values, you could cover all possible tests. But realistically, it is rare that we have a software component or even just a single function where we can test it on all possible inputs. So we got to figure out what we are going to test on. We talked about, in fact, we've just talked about, well, we can at least try to figure out the important cases that we have to cover and make sure that we have 1 or 2 tests that exercise each of those possible cases. And in looking at our testing, we can do some things to try to make sure we've done a good job of testing. And we'll talk about that at the very end of lecture. We can measure code coverage. We can see for our suite of tests, how much of our code got exercised. And we can use that as a measure of how good our tests are. Are they at least covering the code that we wrote? To know if we've tested, again, we can't, the slide is labeled completeness. We can't depend on testing everything, but there are still ways of knowing if we've done a good job trying to test or not, or at least trying to make that argument. Continuous testing is the idea that we're going to do testing throughout our development process. It's not necessarily something that we save till the end of developments. And this can start early in the software process, even when you're gathering requirements. I mentioned I worked with the senior design class a lot of semesters, and this is the kind of thing that we try to get our students thinking about in that class. Even when you're meeting with your customer and trying to figure out what project or what software product you're going to build for them to meet their particular needs, you can start planning on how you're going to test that. Once you understand something about what some feature that your software should have, you can start writing a few tests to make sure that it offers that feature. Normally, software development nowadays is iterative. We don't plan on doing all of our requirements gathering and then all of our design and then all of our implementation and then all of our testing at the end. That we're going to understand the requirements, do some design based on that, and some implementation. And then as we figure out more about the requirements, that's going to let us enhance our design and implement some more stuff. All of those phases on a realistic software project today are going to move forward, maybe not in lockstep, but as you refine your requirements, that's going to let you refine your design. So again, we don't depend on doing all of the requirements gathering before we even start on design and implementation. I didn't say testing anywhere there because the point I wanted to make is testing also can be integrated into the iterations of a software project. As you gather requirements, design, and implement part of your system, you can make sure that you have tests that cover the new software that you've written. Those can either be tests that just look at how your design would behave. Those are going to require some human effort to make sure that the design really permits what you're hoping. But if you've got implemented code, those are things that you could write tests, potentially automated tests for, to make sure that the system that you're building does what you think it's supposed to. In testing a system, there are usually different kinds of tests we count on being able to perform. And this is kind of what I was getting into on the previous slide. I just tried not to say it yet. As you're building different components of a system, and I know you did this in your previous classes, especially in, I think, 216, you thought about unit testing the software you were building. You know that unit test is an effort to build tests that work on each individual component of your system. And component, how you define that might depend on what language you're implementing in. If you're writing something in an object-oriented language like Java, each unit test might try to thoroughly exercise a class you've written. If you're writing in a language like C, you might have to settle for thoroughly testing each function that you've written, or maybe each component of your program, each .c file that you've written. The idea is if we've got separate developers working on different components of our system, we ought to be able to unit test the individual pieces that they've written. Even if the whole piece of software isn't done yet, we can at least know that the pieces we're building each work independently. And that they each do what they're supposed to do. That kind of leaves a vulnerability that I've seen happen a lot, and that is failure when we try to integrate multiple components. I just tried to make the point that even if you've got multiple developers each working on a little piece of a big system, they can be testing, or the team can be testing those little pieces as they're developed and as they're finished. But it's common for things to go wrong when you try to put all of those little pieces together. And that's what integration test is designed to look for. It is making sure that different components work together and that they each do what the other components are expecting. This would, if you're writing in a language like C, this would try to uncover potential flaws, like one person wrote a function and it was expecting 2 parameters, and another person wrote code that used that function and tried to pass in 3 parameters, or tried to pass in 2 parameters with different types than the function was expecting. Those 2 things are nice because when you try to put together those components in a language like C or Java, the compiler will catch the inconsistency. So you won't get very far into integration testing if you don't even agree on the number or types of your parameters. But even if you pass compilation, it's obvious that a disagreement about the details, or I guess misunderstandings about the details of what a particular function or class is expected to do, could still make your software fail at integration time. So integration test is a deliberate effort to put together multiple components in a project before before the project is done, early in the development process, and make sure that they work together to catch potential inconsistencies in that system. And like it says on the middle bullet there, a lot of projects move along just fine until you start trying to put pieces written by different developers together and have them work. I'll say one more thing about this. That's a thing, I mentioned the senior design class a couple of times. That's a thing that we struggle with in that class. We try to encourage teams to get some kind of end-to-end system working as early as they can, even if it doesn't have very much functionality. And that's an effort to try to get some integration testing done early and to uncover incompatibilities between different components of a big system. Even when multiple developers are trying to follow a good process and they're trying to be careful about testing their systems and making sure that pieces work together, things can still go wrong. And this is an example of, I think it's a 1999 Mars Polar Orbiter or Mars probe that failed because of an integration problem. There was one part of the system that was written that produced I think it was a force or an acceleration, and it used imperial units for that. And another part of the system was expecting the result of that, and it was expecting the result in metric units. And these two systems compiled and ran together just fine because they were just exchanging probably a floating point number. And the difference in behavior that they got from the number that was being produced and the number that was expected was small enough that it wasn't actually noticed during testing. But when this probe actually arrived at Mars, the belief is it burned up in the atmosphere because it, over the course of I think a 9.5-month flight, those small differences that didn't make much of a difference in testing ended up adding up to a lot for a longer flight like this. And I would sort of characterize this as an integration test problem, because you had one system that was probably working just fine, outputting a number in imperial units, and another system that was probably working just fine on its own, but was expecting that result in a different unit. I've also got a story about the first death in a Tesla car working in self-driving mode, where the person at the wheel of the car was reading and not paying attention to what was happening while it was driving. And because you can read some of the details there, but it looks like the car monitoring what was going on inside or outside mistook the trailer of an 18-wheeler for what might have looked like another patch of sky, and didn't notice until it was too late that it was actually an obstacle. I don't know if I don't know enough about this particular problem to characterize it as a integration test failure or anything in particular like that. But I think this shows that errors in software, the very software that we expect to write as computer scientists, can cost more than just, well, backing up, I think $125 million in the case of this failed Mars probe, and human life in the case of this Tesla failure. So being able to produce software that we have some confidence in, and especially to catch errors before we release our software, can make a big difference in people's lives, like this particular example shows. We've been talking about various types of testing, unit testing, integration testing. For each of these stages of testing, there are different approaches we can have, and basically based on what we permit ourselves to consider when we're writing a test. Let me just tell you what I'm trying to say on this slide, and then I'll try to fill in what I mean by what I just said. So you're probably familiar with black box testing and white box testing. Even if you're not, I'll quickly say black box testing is where you try to write your tests without any understanding of the code that's going to be under test. So if you're writing black box tests, they would be based on understanding what a system is supposed to do, maybe by looking at its requirements, or I guess if you were testing a particular function, looking at some specification of what that function is supposed to do. Take, for example, the GCD function we were talking about earlier. Even if you didn't know how it was implemented, just knowing what it was supposed to do would let you write some tests for it. In fact, all the talking about it we did earlier was based on just understanding what it was supposed to do without looking at the code. So an advantage of black box testing is you don't carry around bias based on how a particular piece of code is implemented. It helps you make sure especially if a different developer is coming up with the tests, it helps you be confident that what a component actually does is what it's supposed to do. Black box tests can be written based on requirements or some kind of specification, so they could potentially be written really early in the development process, before you've even designed and implemented the thing that you're going to test. But sometimes knowing a little bit about how something is implemented can help you spend your time more carefully when you're writing code. And that's kind of what the idea of a gray box test is supposed to cover. If you look at the readings for this course, there's an example that talks about, I think it's in, I apologize that I'm not certain. I think it's in either chapter 21 or 24 of the text. And it talks about building a system that reads in an employee number and a number of hours worked, and it computes a paycheck amount for that employee. And on that system, it talks about various inputs you could have for employee number, including a bunch of ways that the employee number is might be invalid, if it has too many digits, or if it's got garbage in it or something like that. On that system, or at least on the description of that system, if the employee number is bad, it doesn't even look at the number of hours worked. It just rejects that input. Even if you didn't know anything else besides that, that might help you in writing tests for this system. If you knew that on bad input, the number of hours worked doesn't matter, then you might want to test a bunch of different ways input could be bad, even if those don't have to be coupled with a bunch of different values for how many hours were worked. Since the behavior for the number of hours isn't going to matter if the employee ID is bad. That's what gray box testing is about. It's about knowing something about how the implementation works to let you spend your effort on testing more intelligently. Again, if you've got a bunch of different test cases that all get handled the same way by the program, and few test cases that cover the more interesting behaviors, then that's probably not going to test the system as well as if you had more test cases covering the different behaviors of the program. And again, with gray box testing, the point is you don't need to know everything about the implementation to make those kinds of decisions, but knowing a little bit about how it works would help you make sure you've covered different program behaviors appropriately for how much implementation goes with each of those behaviors. White box testing, as you know, has the assumption that you have complete access to the source code. You may even be the person who developed the source code. And I tried to make the point that black box testing could be good because it lets you focus on what a system is supposed to do and develop test cases that try to make sure it does that. White box testing could also be really good because it lets you see how well your test cases exercise the code. And when we're talking about that, we're talking about code coverage. If you write a bunch of tests and you run them and there are big sections of the code that never actually got executed, then you probably haven't done a good job covering different behaviors across your test cases. So we'll spend a little bit of time talking about measuring code coverage. I know that you've seen this in previous classes, because if you took the C and Software Tools class, we spent a little part of a lecture on that, and we looked at tools for measuring code coverage. And even then, I knew that you were in the C and Software Tools class, I knew that you were coming to that from 216, where I think you also got some practice looking at unit testing and code coverage. So when you're developing tests, you might develop them in any of these three models. Black box testing, gray box, or white box is probably going to involve coming up with a bunch of tests that you want to perform. And each of those tests we would call a test case. And each of those test cases would probably have a few different parts. They would have at least the input to your program or to the component that you want to test. So like on the GCD example, the two numbers that you're expected to compute the GCD of. And they would have expected output for your program. What would be the correct behavior or the correct result from a working system on this input. And then the idea is during testing, we would use the system, we would run the system on each test case, offer it the input that we came up with in each test case. We'd get the output from the system and we'd see if it matched the expected output. If we were doing just black box testing, then we wouldn't need to know how the system was implemented. We wouldn't need to have the source code to the system. We would treat it like a black box. We'd run it on the input for a particular test case, we would get its output, and we would see if that matched the expected results. For looking at black box tests, there are a few things, for writing black box tests, there are a few things that we can do and a few things that we can try to make sure we cover. In developing the test case, we can look at the specification or the requirements for a system and make sure that we've got one or more tests to cover each requirement. We can, in some cases, we might look at the behavior of a system. That might include particular output from the system, the result of a function, or output printed to the terminal. But it might also include transitions on a running system. If we're interacting with some kind of web interface, we might need to confirm that entering a particular value takes us to another screen. And that may be the only output that we're looking for, or doing a particular thing terminates the application. So sometimes the behavior that we're looking for might be a state transition in the system rather than just text or numeric output. In trying to cover particular equivalence classes of input, we might want to make sure that we've covered extreme values in those in each of those equivalence classes, what we normally call boundary cases. If we are looking at inputs that are particular numbers, we might want to make sure we've tested with the largest possible numbers that could arrive as inputs, the smallest or most negative numbers that could arrive as input. I guess thinking back to the GCD example we talked about several slides ago, if I really expect that to work and it doesn't say otherwise, I would want to test it on 2 copies of the maximum int value, and maybe the maximum int value and 1 as the other input. So trying to pick extreme cases in each of the equivalence classes of input. For black box testing, we ought to be able to do all of that, including thinking about boundary cases, without knowing anything about how a system is implemented. But if we know a little bit about how something is implemented, we can use that to test more carefully, to look more, to come up with test cases that exercise the code a little bit better, including looking at system output that may not be visible to an end user of the system. I mentioned if you're testing a web application, some of your tests, some of your black box tests might involve making sure that it changes from one page to another when it should. But for something like a web application, it might also be accessing the database and making changes to a database as you're interacting with it. And those changes may not always be visible to the end user. In gray box testing, you might let yourself look at the state of the database, something a regular end user couldn't do, but something that would let you get more information about whether the system is working correctly, but that doesn't require complete knowledge of the implementation. And that's some of what we're talking about when we say things like system added information. We could look at things that wouldn't normally be visible to a regular end user, like timestamps for when particular events happen, internal state of a system like consumption, amount of memory consumption, number of open files, whether or not files had been created on a file system, whether or not database entries had been created. Being able to look at the behavior of a system at this level of detail doesn't require us to have access to the source code, but it can expose a lot of things that a regular end user wouldn't have access to. But still it can give, and it can give us information that could be valuable for testing. Like I said before, but if you have access to all of the source code, you can write test cases that and you can check to make sure your test cases do a good job of exercising that particular implementation. And there are a couple of ways you can try to do this. The big one we're going to talk about is measuring code coverage. But there are other things you can do based on the internal implementation of a function or, say, an object. If you look at the implementation and you look at how parameters are passed between methods in an object, if you know something about how those parameters are stored, you can use that to come up with additional boundary cases for the tests that might not be obvious to someone who just had the black box behavior of that system. So you can try to exercise parts of the representation that normally you might not even know about. And you can also look at how well the code in an implementation has been exercised during tests. And that's most of what we're going to talk about on our last few slides. In code coverage. Code coverage, if you know this, so I'll try to say it fast. If you've got access to the source code for a system, usually with help from your development tools, you can meter that code so it measures what particular parts of the implementation have been tested. You can measure what statements. Well, let me go ahead and give you an example. For example, you can, with help usually from your compiler, you can add metering code to check every individual statement in your implementation to see if it was executed under test or not. And measuring that is called statement coverage. And I've tried to illustrate this over on the right. So imagine you had a piece of code and pretend every one of those green boxes is a statement. Some of them just compute things. Some of them are flow of control statements like the if and while in there. And if you have access to the source code, you can tell with the help from your compiler, measuring code coverage can give you a report of which particular statements have been executed when you were testing the code. And let's pretend these two red ones here never got executed under test. Now, if that's the case, if these two never got executed in any of your test cases, then that can tell you that you need to add some more test cases to try to make sure those are executed. I guess it's possible that these two statements can't be executed. If that's the case, that's worth knowing, because it means whatever condition lets you access those two statements might be wrong or unnecessary. So if if you've got chunks of your code that never got executed, if you've got statements that never got executed under test, that can point you in the direction of some test cases that you need to add. I'll say, of course, just knowing that you executed every statement under test doesn't guarantee that your program is right. It's possible that one of these statements is a mathematical calculation and it only goes wrong under some particular inputs. But I guess I would say if you've got some statements that never got executed under test, those are statements that who knows if they're right or not. And adding some tests to at least cover those would help give you confidence that your implementation is correct. Statements are a fairly coarse-grained way of looking at coverage in your code. I guess you could execute every statement and still sorry, I've started this sentence. There still may be parts of your program that you haven't really exercised. So there's other kind of coverage we can measure. Branch coverage tries to measure, well, in addition to the statements, how do you get between the parts of your program? And that's what I've tried to illustrate here. If you had a program with a do-while loop, so with a test at the bottom, for that test, you might have a condition or if the test evaluates to true, you might go back and run the loop again. If the test evaluates to false, you would go on and run subsequent code. For other loops or for if statements, depending upon how the condition goes, you might run the body of the loop, or you might jump down to code after the loop. And all of these things I'm saying, like you might jump back to the start of the loop, or you might jump to the next statement. Those are the kinds of things that are very apparent when you're programming in assembly language. You actually have to write the jumps that do that. And even when you're programming in a higher level language, those kinds of things are still there, even if the syntax is simplified for writing them. If you've got a jump, like if this do while loop up here, if it never ran more than one iteration, if you just ran once and then the condition lets you go into the next loop, then that would mean there's a branch, this red arrow I drew, that never got executed under test, which means you don't really know, or arguably you don't know if that loop, the condition on that loop is right or not. Branch coverage tries to make sure that every possible change in the flow of control, every possible condition in assembly language, every possible conditional jump and every possible unconditional jump got a chance to execute, that each of the arcs that connects, every edge that connects the graph that describes my program, every one of those edges got taken at some point during test. And just like there are tools that can let you measure statement coverage, you can usually ask those tools to give you a more detailed report, reporting branch coverage. The conditions on a branch sometimes hide a lot of complexity in our code. And I know we looked at this in 230. There are code coverage tools. So condition coverage tries to look at what's happening inside a condition. If you think about a non-trivial program, a lot of complexity might be hidden inside the conditions on an if or a while statement. And that's what I'm trying to show here in the sample code. You might have compound conditions all over the place. And if you want confidence that those compound conditionals are doing their job, you would like to see every part of a condition get executed at some point during test. Like you'd like to, if you've got an if statement and it's got two parts of it, it's testing some part A ANDed with B, and pretend those are little sub expressions. You would like A to get executed and you'd like the B part to get executed at some point. And for languages that have short circuiting in their conditionals, and most languages have short circuiting in their conditionals, that means that part of the conditional might not be executed. If A is always false, or at least every time you test, it's always false, it's never going to bother even evaluating B. Condition coverage gives you a report at that level of detail. It reports whether every sub-expression in a condition got evaluated. And even there, if you have sub-expressions, you'd like to make sure that they have a chance to evaluate to true and false. Otherwise, you haven't really tested them. So if B evaluates to true, sorry, if A evaluates to true sometimes and false sometimes, then arguably you've tested both ways the A part can go. And if in this condition, if A evaluates to true, it means you will evaluate B. But I guess the same way, you'd like to see B sometimes evaluate to true and sometimes evaluate to false under test. Otherwise, you really haven't tested both of its behaviors. Condition coverage lets you measure that. It can tell you not only the parts of your condition that got executed under test, but how often they got to go true or false. And again, you'd like to see every part of a compound condition get executed and evaluate to both true and false under different circumstances. Tools for measuring code coverage let you do this. I guess there's one more thing we could do. Just because every statement has been executed doesn't mean we found all possible errors. In fact, even this wouldn't guarantee we would find all possible errors. But you've probably had the experience of having a piece of code with multiple paths through the code. And if your code has multiple paths you can take, there may be errors that only happen along certain paths. Like here, I made up a simple piece of code where I'm pretending I've got an if statement up here with a block of code in the body and the same thing down here. And maybe everything is fine as long as you skip the body on both of those. Or maybe if you take the body on the second if and skip it on the first if. But maybe an error happens if both of these conditions evaluate to true. Maybe something happens in the body of this if that breaks what happens in the body of this if. And you're only going to notice that if this if condition evaluates to true and this if condition evaluates to true. There's one more case that I didn't say, but I illustrated it here. Seems like if you wanted to test all possible combinations of behavior like that, then you really need to test, at least for maybe a particular function, all possible paths through it. That's what path coverage attempts to do, or at least measures whether you've tested all possible paths. You can't generally test all possible paths on a big piece of code, because that could grow exponentially with the size of the code. But for small pieces of code, this can help you see if there might be combinations of behavior that lead to an error. And in a piece of code like this, if you've got two if statements, then it seems like you could have 4 possible paths through the code based on how each of those if statements works. And I wish it wasn't this way, but there might be some errors that are only manifested along certain paths through the code. Testing doesn't generally guarantee that our code is correct. And I've tried to make that point a couple of times. The intent of testing is to try to find errors if they exist. We can't necessarily prove our code is bug-free, but we can show that it has a bug through testing. And with enough testing, that could at least give us greater confidence that we've managed to catch bugs if they exist, and we've managed to catch perhaps some of the more common bugs on our system. We can't depend on users doing the testing for us. And that's the point this slide is trying to make. Users will exercise your program, but they won't necessarily try to test for the worst possible cases or the worst possible behavior. When you're testing your own code, or when, say, someone working in the QA department of your employer is thinking about testing your code, if they're doing a good job, they're going to be trying to come up with cases that break a program, that expose flaws if they exist. They're going to be trying to stress the behavior of the program, and that might mean things like running a bunch of copies of the same program at the same time to test for different performance, or letting the program run for a really long time to see if memory leaks, to see if, say, a slow leak in memory uses up more and more memory space as the program runs. Most of the time when we're thinking about testing a program, we're concerned with the correctness of the output, or the correctness of the behavior if it's not, say, terminal or file output. In some cases, our requirements might have performance components. Maybe it's not enough to just produce a correct output, but we've got to do it within a certain amount of time. And on, like in your operating systems class, you'll talk about real-time systems where some of the correctness depends on execution time. Not being able to produce an answer fast enough can make that answer worthless to the system. Most systems, we don't necessarily have to worry about performance results, but on some systems, measuring performance can be part of the testing we need to do, and they can be part of the correctness of a system. An interesting thing about this is if performance is part of your correctness criteria, then tests that used to pass might not pass anymore as a system is extended and enhanced. Usually as we add features to code, as we add new behaviors to a system, it gets bigger, and as it gets bigger, it often gets a little bit slower. If a system's getting slower, then some performance tests that used to run correctly might not meet the performance requirements anymore. So for even with no change in our program's output, it's possible that a performance test might pass on one day, and then 6 months later, after a bunch of code's been added, that performance test might fail. Tests that fail like this are usually called regression bugs or regression errors. That means that as we added things, as we made changes, stuff that used to work no longer works. On a system that has that's being maintained, new features and new code are going to be added to that system. If it has correctness requirements in terms of performance, then those need to be part of the regression testing on the system. We need to not only test to make sure that we continue to get correct output on the system, but we need to test to make sure that it runs, that it meets the performance requirements moving forward. And I've pointed to senior design several times. Lots of teams have to worry about this kind of thing, not necessarily the regression component, but they have to worry about testing to make sure not just that their system produces the correct output, but that it runs fast enough for what their customer intends to do. And that is all that we're expected to talk about today. I'll invite questions like I usually do. We finished up about 20 minutes earlier than we usually do, which is fine. We've got a test coming up. Are there any questions about the material I've just tried to cover or about the upcoming test? I'm still recording to get those questions, but I'll stop recording in a moment and see if there are other questions that people don't want recorded. Any general questions at this point? Someone just put something on the chat. I'll take a look at that. Looking at the questions on the chat, we got a question about what will be covered on the exam. And it does go up through the end of today's lecture. So I would say the stuff that we covered today is fair game for the exam. Oh, I got a question about the lecture. I was going to post this in the week's notes, but I can go ahead and say, Wednesday, we will not have a new lecture. So we're simulating face-to-face meetings. So on the second lecture of the week, we're pretending that's replaced by the exam. So we'll just have one lecture this week and we'll pick up lecturing. So lecture 11 will be on Monday of next week. The first post said you should also probably try switching, but I didn't get the rest of that, so I don't know what. Maybe I was having some trouble with the system there. All right, I'm not hearing or seeing any new questions, so I'll stop recording, but I'll hang around in case anyone has some other questions.